You were talking right here about the, oh, where did that go? There it is. You're talking about the ASCII animation line, right? Okay. So let's start on the right. So if we group this up, we've got our input here. We've got this power operator, which is a dyadic operator. It takes a left and a right operand. The right operand is this equivalence function. That's a dyadic function, 2 arguments. This guy here is the left operand to the power operator. This guy is applied after everything. So after the power operator returns, we apply this nil operation. It's like a blank function, a lambda returning nothing. This guy? That's power operator. So when this power operator is, you can think of it like a functional while loop or a fixed point iterator. And so what it's going to do is it's going to take the right argument, apply it to this function, get a result back, compare it to the original argument using equiv, and then if the 2 are equal, it's going to stop. However, if they're not equal, it's going to take the result that we got from that function, apply it back to this function again, and repeat.
It's taking then predetermined parameters.
Operator? The power operator.
Yes.
No, it's taking 2. It takes this function on the left and this one on the right, put parentheses around that. It derives a new function. It returns a function that then gets applied to the RR. Right. So that's, again, the distinction between the function level and the expression level. The expression level is worked with after the functions have been figured out, once we identify the functions. So the functions are figured out, compound functions are figured out by parsing the operators and how they're composed together. And so then once we have that inside of this guy, that runs every single time. So this is one statement, a second statement, and the last statement. And because this last statement does not have an assignment, that's going to be the implicit return. So you can think of that as an implicit return at the end there. And then what we do is we take this expression and bind it to pick. The extra compose there is a special symbol that says update this variable in any of the graphics. Or basically it says update the state. Send a signal to anybody who's been waiting on updates to this array so they know what to do with. And primarily, this is a controversial little hacky thing for the IDE inside of the language. And it's very useful for stuff like this. It's not exactly the most pure of APL, because it's kind of side effecty and not mathy. Then, remember that omega refers to the right argument of the function. Then we have this function here, which applies the reciprocal of 8, or applies DL, quad DL, which is a system function. And it applies that to the reciprocal of 8, which creates a delay of 1/8 of a second, and then returns. However, if we want to avoid returning this and not evaluating this, we have to bind it. So we bind it to a blank. So we can say we're still doing stuff in this. You can think of it as how you might use letrec star or other kind of let bindings and step by step do something. And so if you want to just compute something as a side effect, in that case, you would just give it a blank name or some junk name. And then finally, we run life and we return it. And then it cycles on again and again and again until the thing that we passed into the function is the same as the thing that we got out of the function, in which case we've reached our fixed point and we end. Is that what you were hoping for?
I guess so.
Is anything still unclear about that expression?
No, I'm just wondering about the power operator. The examples of the power operator on dialog are very different from what they do there.
Probably. Why does it always disconnect me? Thank you. So the power operator takes 2 different types of arguments on the right-hand side. If you pass it a piece of data, it iterates a specific number of times.
Oh, okay. I need to pass.
If you pass it a function, it's like having a test condition in a while loop. Except it's while this is false. So it's more like an until loop.
So if the object being returned is false according to APL,
The object being returned.
like a 0 is false.
Yes. Yeah, so these examples here. Yeah. So in these examples, yeah, so the CAP, conditional application, is an example of a common pattern that's used in APL, which is to say, I want to apply something, but I only want to apply it if this other thing is true. So this is, I would consider this the kind of thing that you only put in your applications if you really need it, but it's a very common thing for people to work with so it's a form of conditional application. So your alpha there is going to be your test, and then you run the omega. So the way that would work is, they've got an example right below it, yeah. So the way to parse that example, let's actually execute that example because this is a good demonstration. So ABC was defined to what? We better run that. Where did ABC get defined? Oh, it's just a string, I think. Yeah, so a string applied each over the other stuff. So then the function they're using, so in the operator syntax, what's this junk out here? Yeah, there we go. And there we go. Okay. So let me just print out this guy. Okay. So in this one, alpha alpha represents a left operand of an operator for a user-defined operator. And so then so the alpha alpha is going to be this enclosed expression here. And then that's going to derive a function or return a function where alpha and omega are used. And so that function is then going to be passed into each, which is going to derive another function or return a function. And that final function is going to be applied to 101 and the right-hand side, which is a vector of strings, each string A, string B, string C. And then what it's going to do is it's then going to say, all right, alpha is 1, so we're going to apply the enclose operation on it. Or in other words, we're going to iterate once. And then B is 0, so we're going to iterate 0 times, which means we're just going to return what we received. And then on this one, we're going to iterate once, so we'll apply the operation once, and we'll enclose the C, box it up. And so if we had done this a few other times, let's say we wanted to actually provide more than just that, we could put a 2 here. And so now the first one is boxed once, the second one is boxed 0 times, and the third one is boxed 2 times.
Alpha is the left-hand.
Left-hand operand, yeah, which would be a function. And alpha is the left argument to the function that's returned from. So a way to think about this, if I use some scheme ideas, is lambda alpha alpha omega omega returns a lambda of alpha omega. So this is the operator we're defining, and then this is this is what appears inside those brackets, this stuff here. Yeah. So then we're doing this guy on this guy with this and this, and then this. So if we put some white space in here, there you go. Does that make sense? You still look like you're not fully.
In this case, the power is still being applied to
Data value.
data value.
Yes. So if it's not applied to a data value, what it does is it's asking whether the value that we're iterating over is reaching some point at which the things are fixed point or something. So I like to call this one power limit because one of the common ways I use it is with the equivalence operator to run fixed points. But you can, so that runs it until they're the same, or you can use not equivalence or not match to test it until they're different, or you can write your own arbitrary functions in there and test any number of things. Such as, maybe we're approaching 0 or something like that. Okay. So how's everyone feeling? Good? Ready for more?
I only got an APL working.
And
Skips I haven't done.
an APL working?
And APL.
Ah, Maple.
Yeah.
Okay. I thought you said an APL, and you really scared me. Like if you're running one of the different APLs, you'll be sorely disappointed.
One last thing.
Yeah. Don't make it the last thing. Keep asking.
The open-close curly brackets at the start of that expression.
Open, close. Can you point to which one? Oh, yes. So that's a function that returns nothing, but takes anything. So what we're doing is we don't want to print out, because we're on a REPL, we don't want to print out the result of computing that expression. So instead, we want to discard the result.
Okay.
Yeah. All right. So I want to have you guys writing code pretty soon. Any other questions about what we did this morning before I start going into philosophical manifestos, at which point we will then start writing code, after which point? You said you'd already seen the video, right?
I'm excited for you to do it again.
Okay. Well, I'm going to try to simplify it and make it not 3 hours long this time. So, but last call for game of life questions, unless you'd start doing the biology problem set. All right, you're all intermediate APL experts now, so let's begin doing the good stuff. So let's go to this. So this page is a little bit of stuff to work through, but we're going to go through it here. Basically, now you guys are all at the point that you kind of can muddle your way through figuring out literally what an APL expression does. Probably, with some testing, some swearing, and some confusion, coffee. Actually, speaking of coffee, excuse me. And you can probably type in some APL expressions, right? So, for example, there is the Fin APL idiom library. Let's do this one here. So we just wrote the game of life, right? What if you had an entire book full of one-liners? that you can play with. So right now you're at the point where you could go and say, oh, I want to see what kind of problem I want. And you could go and work your way through. So, oh, you want to interpolate values of a series at x, y, g. Okay. Oh, I want to do the curve fit points or linear regression or any number of things. Okay, I've got a one-liner to do that. But you'll have no idea how to write these yourself. The difficulty comes in writing one of these because you can sort of read this. You'll probably be able to work out how it works and you go, oh, that was really cool. But then when you get to scaling up to complex problems, you're no longer able to just pick one of these and make it work. You now have to understand how to make real APL software. So just to give you an idea, a statistic I like to quote is one of the people that is a heavy user of APL, I believe has a source code of 1.3 million lines of APL. Is that right?
Yes.
Yes.
What would that translate to a C level? 12 million?
And they still like the language after that many lines of source code, give or take. I'm sure somebody in there is not happy. But you know, for the most part, I think it's a relatively favorable impression of APL, even after 1.3 million lines of code. Now, it is not 1.3 million lines like this. They have a style that they're using and a thing that works for them. But if they could write all of their code like this, they probably would, because it would shrink the code base significantly. Sometimes they're using structured primitives, control flow, things like that, where maybe they could get away without it. But at the moment, that makes sense. So, but how do you go from here to one of these large code bases? How do you go from here to something else? And to make this work, you have to understand why APL exists in the first place and why it's used. Because the reason people succeed with APL is because they're using it in a manner and they're using it to solve problems that don't, in ways that don't fit the standard mold. And this is the problem, is most computer scientists struggle to understand APL at its heart, you know, sort of metaphysically, because they're trying to look at it semantically. They understand the semantics, which you guys all now basically understand how APLs work, you know, arrays now fit together in an APL context. But what you don't understand is, or well, maybe you do and you're brilliant, that would be great. But you know, for most people, the problem is in trying to then apply your traditional computer science background to writing APL code. So most of you here will have a fairly good idea of the traditional design patterns and best practices that are used in other software and other languages. Things like clean, non-leaky abstractions, right? You need your abstractions to be non-leaky. You want modularity, reusability. You want to make sure that you write your code in such a way that you don't have to see the whole code base because it's going to be too big for you to see the whole thing. So you need to make it so that you can look at any arbitrary piece of code in there and sort of reason about it locally without having to know too much about the rest of the world. So you do a set of techniques to try to encapsulate that one piece and parameterize it from the outside world so that you can reason about it. These are all standard best practices among industry, among software engineering, among functional programmers. You know, you do this all the time. You do good data type abstractions so that you're not munging things and you've got functions that work specifically over the right type of data so that if you happen to try to do something and you get the wrong data, you get a runtime error, you get a type checker error or something like this. These are all things that everyone in normal computer science considers good things. These are what I call anti-patterns in APL. So Iverson envisioned APL as a notation for solving mathematical ideas or as a notation for thinking about problems, for teaching and communicating ideas to people. So the first thing you have to get across is that this is not a language for machines. This is a language that happens to execute on machines, but the critical part about the language design and the perspective of the language is how do we make sure we can communicate ideas effectively to other people? And that other person might be you 10 months down the road. And so the notation is meant to facilitate reasoning about code at this level and a human-to-human exchange. That's why it's called a tool of thought, usually. And in Iverson's Turing Award lecture, he listed a set of 5 principles that he felt were important to notation and a good computer science notation. Ease of expressing the constructs. So in other words, you should be able to write what you want fairly easily. Suggestivity, which is a very interesting one, because what he wanted was a notation that when you saw it, suggested new solutions, suggested new ideas, suggested ways in which this piece of code or expression might apply to other domains, cross-domain transfer of expressions or code. Additionally, we have the ability to subordinate detail. Now, that might sound like abstraction, but I would like you to consider this as separate from the concept of abstraction as it's used as a technical term in computer science today. Instead, ability to subordinate detail is an ability to free your mind from details that aren't necessary to the problem. And potentially a detail might be abstraction. So in addition to this, economy was important. Economy means that you should not find it difficult to express what you're wanting in a small amount of space. You want it to be notationally efficient or syntactically efficient. So notation and syntax are very closely aligned. And you want to be able to write something down efficiently. Now, I translate economy into the whiteboard test. So in other words, think about the code that you've written recently, large things that you're kind of proud of. Now, what if you were told you only get a whiteboard, you only get a piece of chalk, you only get to write code that you have actually written in the thing, and you have to explain your code to an audience. You're not allowed to use pictures. You're not allowed to run demos or anything like that, and you have to write the source code out, and they have to completely understand the full implementation. Most people never do that, ever. However, in the APL domain, this is the common way of working. You very often see people communicating back and forth with nothing but source code as their primary means of communicating ideas between each other with no other additional tooling required. And that's an important aspect to APLers. That's an important part of what they consider APL to be, is a means to do this sort of communication. And of course, amenability to formal proofs in Iverson's day, before the large-scale explosion of automatic proving, was the ability to do symbol pushing on your code as a method of playing with it. So algebra with your code. And most code is not very easy to do algebra with, if you've ever tried. Automated proof tools have made the proving of code much, much better than it used to be. But if you've ever had somebody try to write down what they did to formally prove something on a whiteboard, you'll find it kind of somewhat scary. So they haven't actually made it easier to read the proofs in some sense. They've hidden it away and let computers do the reading of that stuff rather than make it the language itself able to play with the proofs. So back to this idea of what are best practices in the computer science community. My claim is that when you guys try to learn APL, and you're going to do that more moving forward, when you try to do this, you're going to try to use every tool in your toolbox to understand this weird language and to make it work through the eyes of what your traditional best practices say you should be thinking about. And I'm saying that will be the absolute best way to fail miserably. Because in APL, not only do we do things differently, when we're doing array paradigm programming, we're doing the polar opposite of what you were trained to do. And that's how we make our code better. And this is where it gets difficult, because you're going to want to do certain things. But over time, those things, those habits that you have, my claim is that you will actually find that makes APL programming seem much more difficult than it is. So let's go through these. There are about 8 of them. Macro versus micro is the biggest one. Most people, when they work at the program, try to break the problem down into smaller bits, think of them at the smallest level of detail necessary, and then compose it back up using control flow. APLers do the exact opposite. They try to make sure they are not going down and are staying at the macro level as much as possible. So for example, in doing a tree traversal or something like this, the normal way people think about this is how do we hide all the macro level considerations and then focus just on what we do per node. So this would be pattern matching in Haskell, NanoPass, DSLs, things like that. We do all this work to make sure we focus only on the micro piece. APLers instead want to hide all of that unnecessary low level or small micro per node detail and just say, well, for all the nodes, we just do this. Don't worry about what the other stuff is. So they stay at the macro level. They try to look at the big picture, see the whole picture together, and try to avoid as much as possible the micro level, and only go down if it's really one of these things that you have to break apart in order to really make sense of it. So the more that we can keep things at a broad overall stroke without thinking about individual units inside of our code, the more the APL code becomes more accessible to us. Next is transparency versus abstraction. And this is a controversial one. This is one I like, though. And my catchphrase for this is abstraction considered harmful. And any Haskeller in here is immediately about to burn me at the stake. And with good reason, actually. Abstraction is extremely useful. And abstraction is there for good reason. And abstraction is, in fact, necessary to write good code in other languages. However, abstraction in the style of the other languages fails us in APL because abstraction requires distance. It requires indirection, and it requires the creation of a connection of linkages that grow in their distance from one another over time. And what happens is that we lose the macro view. We lose the ability to see the whole system. And because of the economy of the notation of APL, we're often not using names efficiently. And we'll get to the naming part. But basically, to an APLer, it's much better to see the underlying implementation and to know what's going on under the hood than to have an abstraction hiding that away somewhere, creating a hard boundary. This is similar to Knuth's complaint about libraries. He was famous for complaining that libraries prevented him from making edits and tweaks to the underlying implementation. Similarly, if you have a function which is 4 characters, which implements the average of a vector or a matrix or other things like that, then it's not very efficient of your time to create a utility function called average, which is almost twice as long as the implementation itself, and then use average everywhere. Because now you've just made it more difficult to see the code. You've made it more difficult to know what's going on, and you haven't exposed the edge cases. So APLers use transparency instead of abstraction. By showing more of the code, it's at more of the surface area of the actual computation of the code, we can see more of the edge cases, the special things we have to consider. And we don't have to actually go back to documentation and say, oh, well, so how do you handle the 0 case? How do you handle the boundary cases, et cetera? Because it's right in the code. Yes?
So that velocity, do you end up with more duplicate code, as in?
Yes.
Okay.
And I can show some examples later on, once you guys are a little more familiar with the APL, why I consider that actually a good thing. And this is, again, one of those anti-patterns. Normally, code duplication would be a horrible thing. But in APL, code duplication is similar to naming, because our code that we duplicate is just about the size of what most people would use as a name. So the length of the code is about the same as the normal symbol that you would use. And your mind now learns to chunk that thing. And so it no longer becomes an implementation. It becomes a symbol in your mind of an implementation, which is encoded in the name itself. And as an example, average is a good example of this, right? So what is this? OK. All right. So average in APL is that. Now, that to an APLer now gets chunked. That's not just an implementation of some code that you now have to figure out what is the higher level meaning. To an APLer, that's the name for average. That's what we call it. We just call it its own implementation. So then we scatter that throughout our code. That's a lot of code duplication. But it's also just a name to us. So it's not really code duplication in our heads, because the name and the symbol is the thing that's all the same thing. And this is more efficient to us because now that symbol, that icon of average, becomes the unit by which we work, and we can see it all without having to have any barriers or indirection that prevents us from seeing the whole picture or may allow something to get in the way.
But if that becomes larger and I end up having a mistake in that piece, I mean, obviously I just have to go fix it.
Yes, you would have to go fix it everywhere. And that could be scary, but it's actually, in principle, much less scary than you might think when you write certain code. Now, this is not always true, and I think more.
You're not saying that you never name.
Yes, I'm not saying that you never use a name, and we'll get to that. And in fact, names are very useful, but the difference is we don't raise the abstraction level arbitrarily through our code. We have an abstraction level, the hard barrier at the bottom, and we try to stay at that abstraction level the whole time. We have our domain layer, which is our other abstraction. We try to stick in those two domains, and we don't create this intermediate barrier, this intermediate pyramid of interconnecting abstractions that form various models. So, for example, a UML diagram in an object-oriented programming space would be a classic example of this, right? Tons of abstractions trying to communicate an idea. We don't put those intermediate abstractions there. So what we do is we use names differently. So we'll get down to names. Well, we'll get down to names. The next one is idioms versus libraries. That average function would be considered an idiomatic expression for average. So rather than using a bunch of library calls, APLers historically have tended to use idioms. So that's what idiom list you saw. And the reason the idioms are useful is A, they're very, very short. B, they allow us to modify them and tweak them to fit whatever our unique special case is, but they remain structurally similar enough that it's easy to identify what we're doing to another APL programmer. So like, oh, you're doing 2 not equals reduction over this. That's an idiom for a certain set of problems that APLers know that's how you can do these sorts of things. And so it becomes a way of communicating to other APL programmers your ideas without using extensive library API calls with very, very long names. Because most of these APL idioms that are implementing these things are much shorter than, say, their Java names would be in the Java library. Whereas other languages, particularly object-oriented programming languages, are heavily focused on large, complete, complex names that give you a lot of information but subordinate and hide what's actually going on under the hood. And then we have data versus control flow. So the APLers have a very strong preference for using data to control what's happening in the code rather than using control flow. So if you can express it without having to use control flow and instead using data to express the logic of your code, then APLers tend to favor that significantly. And structure versus names is going back to a little bit of the transparency versus abstraction piece. But APLers often, in most other languages, you use names as anchor points to help you show what something is doing, show you how it puts together. So in Java, a classic name is used words like factory to identify this is the implied contract that's going to happen in this. And you use that in Scheme, too, with things like hook and other things. Inside the name, there are these little type annotations that tell you what we're dealing with in the code. In APL, we like to have the names shorter and instead rely on creating structure in our code that reveals that kind of intent. So for example, the use of inner product and these operators like power and other things allow us to sort of perceive the structure and the way the code data flows through the code without using names to sort of identify that. Concision versus verbosity ought to be obvious, but we definitely feel that it's better to be able to see more of your code than to be able to see less of it. And implicit versus explicit. We often prefer for behavior to be implicit rather than explicit. So we will do things many times that might be considered slightly dirty because it creates the ability to do an implicit behavior rather than an explicit behavior. Because in this case, it doesn't matter. And because we can tweak things individually, we can adapt them for individual situations and not really lose the ability to see the big picture of our code. And then the final one, which is going to be a very big one, and which I encourage you to think about a little bit, is syntax versus semantics. Most of the computer science sphere focuses on semantics. The syntax doesn't really matter as long as it's interesting what the code gives you, what it's doing, what are the runtime guarantees, what are the type level guarantees, what are the optimization guarantees, what's the memory performance guarantees. That's all semantics. In APL, you ask yourself, well, how does this feel? What is the aesthetic? Does this look right? Does it look usable? Does it meet the goals of the visual experience, the process of working with this code? And those are tied together with the syntax. So in APL, there might be many, many different ways to do something. But the one they're going to choose is the one that's syntactically most beautiful, if they can get away with it. Because that's the one that's most usable and the most readable and the most beneficial to the APL programmer when all of these things fit together. Yes?
Do you not care about semantics?
we tend to keep the semantics as simple as possible so that we can focus on syntax. So for instance, are you familiar with SICP, the Structured Interpretation of Computer Programs, Adelson Sussman? Who's read that book? Okay, there's an introduction in that book. They go over why they think Lisp has succeeded in certain domains at the time, where it was in the AI heyday, say, versus some other systems, which were more imperative or object-oriented or some of these others. And their argument, or claim, it's not much of an argument, is that with certain programming languages, you're building pyramids. So you're building systems that have to stand the test of time. So reliability and ability to resist change become critical. Ability to resist breakage become critical. So, for example, a classic version of this would be the Clang compiler, Clang, which uses tons of very cool, sophisticated tricks inside of the system to make sure that if you change something, it's going to break and warn you if you haven't done all the things necessary to hook all the pieces together and make sure it's all correct. Because the system is so interdependent, it's this interlocking grid of very resistant bricks that create this very pyramid-like structure. They would argue that the Lisp structure instead creates this amoeba, this organism of very simple cells that's constantly evolving and changing, and it has no definable shape or structure that you can sort of get a hold of. And one of the ways this falls out inside of programming is the use of types versus data versus functions. So in the Lisp style, it's often very nice to have one data type over which you have 100 functions, as opposed to the pyramid style where you have 10 functions over 10 types of data. And in APL, we're more as the Lisp side. If we can have one data type and 100 functions to work over that type of data, that gives us more power. And it gives us that Iverson concept of suggestivity. So if we're in the tree domain and we have all this data types for trees, we see trees. We don't see, oh, is this actually just the same thing as this other domain? Because we've isolated that domain in our heads by so much. In the APL style, when you're doing this, oh, trees are just the same as this, which is the same as this. The exact same processes apply across all. The exact same code actually works across all of these. So the code for doing various things like string processing, tree processing, grouping, databases, all this stuff, actually uses very similar code structures and things that appear out. And so we have these general functions that work across these domains. Whereas traditional, say, very strongly rigorous types of computer science would say, no, you should separate these out into very specific type-oriented or type-directed functions that work only over this specific thing. And that's part of where this syntax versus semantic thing kind of plays in, because we want to leverage the syntactic aspects of the language more than we want to leverage the semantic aspects of the language. So data type abstraction would be a form of semantics that may have good syntax on top of it, but often encourages lots of semantic playing, as opposed to syntactic playing. And so when you go, we're going to go and start playing with these programs. I want you to think about these patterns when you're looking at it. And try to let yourself think about using the patterns on the left here, rather than what's more comfortable, and which is on the right for most people. Now you might be different, and if you feel like this doesn't apply to you, I'd love to hear about it, because I'm very interested in the HCI. My PhD minor is actually in learning sciences with an HCI focus, or an HCI with a learning sciences focus, and the experience that people go through when they work with things like this. And so the experience of programming is important to me, and how you think about it, and how you engage with the code as a visceral physical object, and play with that. So, think about that when you're going through it. And so what we're going to do now is you can go through, and each of these domains here has a set of problems, maybe some extra stuff at the top, stuff for you to play with. And it's going to start basic, and they get progressively more complex as you go through the problems. Image processing is a fun one of my favorites, but you'll get to work through images, do stuff like that. You can play with any of these domains. We've got mathematics, Mandelbrot sets, biology, chemistry, physics, graphing calculators, all sorts of fun stuff. And so just pick any problems you want, start solving the problems, and see what you get. And if anybody wants to work with some of the graphics stuff, then you'll need to make sure that you have loaded in your CodeDefense workspace and have run a couple of things. So I'll show you what that looks like. But otherwise, go wild. Have fun. And if you have any questions, we can talk about it. So, yes.
What is suggestivity?
Suggestivity is...
And you can give an example.
Yeah, so inner product we just saw in the game of life, right? So you have plus dot times. That's matrix manipulation, matrix multiplication, right? But the inner product operation, you think, can that be used for other stuff? So when we see plus dot times or dot and, we can ask, well, can this actually be used for something else? Can this, what if we swap them? What if we swap the and and the or? Is that a useful expression? Does that lead us anywhere? And it actually does. Plus dot times, what if we change plus dot times? Is plus dot times the same as, say, exponentiation and logarithms? Can we put those in? Can we lift multiplication to exponentiation and lift summation to multiplication? What does that do? Does that make sense? Things like commutative properties. We can sort of see commutative properties inside of our code and say, oh, does that work? Or let's say we have a string that we're partitioning things into, and we have to scan over them. And we go, oh, well, what if we change the data a little bit? Does it work? One example's, I don't want to get into it now because I want you guys to play with the code, but later on today, remind me, and I'll discuss suggestivity as a part of how I got into the specific research focus that I'm doing, which was how to execute a compiler in parallel on the GPU. And I only solved this problem, my claim, is because of the suggestivity of the notation of Iverson. So APL allowed me to actually solve this problem in a way that I was struggling very, very hard with figuring out how to do. And I discovered this solution that the suggestivity of the notation and visualization of the data allowed me to solve that. So a little bit later, when you're a little bit more familiar with how to make the code go, I'll explain how that actually, how I used it. We can see that.
That compiler, is it for your own custom language? Or is that for
It compiles defuns, this language. It compiles APL in the style that I've been showing you here to the GPU and the CPU.
Okay.
And it's written in this language. It's written actually in a subset of this, which
Do
is...
you have dependencies? So I'm not familiar at all with APL. Is this APL dependent?
It just relies on the dialog interpreter at the moment. It's close to self-hosting, and it uses the array-fire libraries in the backend to achieve some of the
Yeah, but I mean, you're
portability.
compiling code, and usually it's not parallelized code because, you know, X might depend on Y and Y depends on Z. So chicken and egg, or basically have to compile Y, then compile X.
Oh, in terms of modules?
Yes.
So I only do single modules at a time. Yeah, and they have to be, there can be no free variables at the module level. So it has to be closed modules.
Okay.
Yeah. It's not impossible to do it otherwise. In fact, there's nothing holding the compiler back about doing that, but there's just no performance gain to be had in doing it that way. Yeah?
Do you recommend going through these in order or just picking one?
Any which way you want to go. However, oftentimes the problems before one problem will give you the tools necessary to solve the next problem.
Sorry, I mean, so if you pick a domain.
Oh, the domain. Yeah, just any domain you want.
Any domain.
Yeah, solve as many of the problems or as few of the problems as you want. If you get bored, go to another domain. Look through the problems, see what you want to do. Yeah.
I'm in the end of the matrix.
Yes.
A key, arrow expression. Why does it update?
It's just a little trick that's put into the system. It's a type of assignment. So there's what's called modified assignment.
Okay. So it's
And-
not the circle is not.
The circle is a jot.
Yeah. It's not composed. In that.
No. It's composed most everywhere else. It's used in a few places where you need a graphical sort of mnemonic. This is where it's used a little bit as a graphical mnemonic. It's in outer product. So outer product, the compose, the jot is on the left-hand side of the period. Yeah, it's also a little bit of a graphical mnemonic, sort of saying this is like inner product, but not really. I don't think that has to be a global assignment, but it will update state for the editor.
Right, but a normal assignment would do that too. It's only when you have it inside the...
Oh, inside, yeah. So,
When you have it in the body of the defund that you need that, because otherwise it would be a local...
right, that's a good point. So defunds scopes the variable. So variables defined inside the lambda are going to stay inside the lambda. And so because of that, assigning to pick there would refer to a local variable, not your global variable.
So you don't need that in the global thing.
Yeah. So if you were just updating it in the REPL session, you wouldn't need it. Yeah. Yep. And we'll go around and help you. If you get stuck on anything, play around. I don't guarantee you I'm going to give you the answer, but I like you to sweat for it. But yeah. Yeah, it's a little bit controversial as a system, but it's useful to play with a little bit. And if anybody gets really far along, I would love for you to tackle audio processing. I don't have anything written on it, but I've done it once, and it's very fun. But that's just a little candy to offer you if you get enough experience.
I mean, APL interpreters is you can write one in like 3 weeks. There are papers that say how to do it. But writing a fast one takes 30 days. And then they do AVX, and then they. So we have people working full time.
Even then, it was only one part of knowledge.
And big booleans. So those.
I do want to, because I love the enter the matrix one, I'm going to, yeah.
And Damus Goss teaching that, and he was just talking about how mathematicians don't really care about syntax. And I think that doesn't transfer to programming at all.
And mathematicians should care about syntax a lot more than they do.
Yes. And I think that's changing a bit with category theory compared to lambda calculus.
Potentially. Iverson was a big proponent of focusing on notation. But mathematicians have been doing that for a long time too. So yeah.
I'm saying, because I'm a Scala programmer, so I need to annotate all of my types.
My condolences.
Yes, thank you very much. I do appreciate that. And it makes things so hard, you just don't want to do them. And people really misunderestimate, if you will, forgive my usage of that term, how important that is.
Yeah.
So, yeah.
All right, let's see if everybody's, I'm going to put up a little thing for the enter the matrix, so let me, yes.
See that page?
Oh, you've got it online. If you go to your Slack, go to Slack where we had it, and go to the functional array channel, and there is a link to go to all the materials, so you can pick out whatever one you want. So if you go to the functional, where's the functional array? You might have to add the channel.
Oh, I see.
So you're in LambdaConf, that's why. You go to functional array.
Yeah. Yeah, so I'm hearing a couple of people asking about this. There's a functional array channel in addition which contains the links to the stuff.
Or do you need to use the
And that materials link at the top should be globally accessible to anybody with a web browser. Yes, okay.
Hey, so I want to try and mess with the parsing stuff.
Yeah.
How do I act on strings?
Strings are just surrounded in single quotes.
And is that just a vector?
Yep.
Like
You can get the shape of it or anything like that. Numerics will give you a domain error, but other than that, yeah, you're all good. Yes. It might help if you go along the edges, so we don't have to climb over.
Yeah.
Oh. All right. Where's our tech coordinators? We need more power.
Power is what's driving
We need more power. Well, it'd be nice if they could work on the edges here, and they don't have power connections that go out this far. Okay. There's another power strip up here if you want to go there. Or are you working together?
No, I just
Yeah. Yeah. No. I'm suggesting it so that we can so I can look at your screen easier.
I haven't done
Yes.
scheme in a long time. I'm assuming you're defining Linden as having a connection to this guy and that
To those
guy,
two, yes.
And then this guy's
Yeah.
having
So
a
the
connection to those
first
two.
element would be the thing,
thing.
and then arrows pointing to each of the things. Yes. Yes. Yeah. Sorry. I scheme it on APL. I don't do the other stuff. Well, I'm from the Kent Dybvig School of Shea Scheme, so that's. Oh, which professor? All right, no problem. Gonna mute the audio. Okay. Good question, good question. I did want to just show, for the people doing the enter the matrix domain, what they can expect. So here's kind of what you're going for in terms of your matrix function. So that's what you should get at the end of your matrix domain. Sorry? And at the end of image processing, for instance, you'll be able to make Obama icons of yourself, and you'll be able to do a blur animation of blurring an image. And at the end of the mathematics domain, you should be able to make a Mandelbrot set animation. At the end of biology and physics, you should be able to do graphing calculators and animate graphs like cannon fire and things like that. At the end of biology, you should be able to make multicolored games of life on toruses and Mobius bands and things like that. So, yes. Yes.
Is this range here supposed to be 254 instead of 54?
Potentially.
I think it's
Play with that. Play with the quad AV.
Is
And
it the right
see
way
what you
to
get.
get the characters? Like that?
Well, that's one way.
One way, okay.
Yeah, there are many different ways. So play around with it and see if there's different ways.
What does it mean to create a pattern for the background?
So creating a pattern would be just to play around with populating that grid with a background image. Maybe instead of a blank image to start with, you want to start with periods or dots or circles.
Where's the DFNS workspace?
So if you are accessing defunds, built-in defunds library helper things, you're going to write copy defunds, whatever your function name is. And that'll pull in the defund. What? Yeah. That's sort of out of the scope of what I think we should go over, but you can use the IDE to explore that.
Oh, so I didn't know if there was just like a user doc of what's available.
Yeah, so if you want to see what's available in the defunds, yeah, so if you go to defunds.dialog.com, you can see that. I encourage you to try to not use, don't use the library mentality. So if you can, don't use pre-written functions for this. Try to explore the code as its own rather than using the existing stuff.
Well, and you have like this get UTF-8.
Yeah, so UTF-8 get is one of those where I'm okaying it.
You don't have to write your own UTF-8.
Yes, you will not have to do that. Quad UCS is also your built-in UTF-8 decoder, et cetera. So there's some hard barriers which we're going to accept as library calls. Those have to do with UTF-8, XML, and JSON, and PNG images and JPEG images, things like that. So CodeDefunds has a built-in image loader. So if you're in the image domain, you're just going to load the image in. I'm not going to make you parse JPEG. So, yeah.
Is it wrong to assign the character sequence to a constant, a variable?
Let's see.
Like if I want to assign this to the right like that.
Yeah.
Is that fine, or
Yeah.
does it violate the?
Well, just play with it. Just see and think about, does it violate the principles or not? See if you think it does or not, and we can talk about it as your solution comes out.
I don't want to be spoiled with my...
Well, so do with it, see of it, and look at it, and then what we're going to do is we can demo some of these out. We can play with some of these, and you can see some of our solutions, what we decided to do, and we can code golf them, find ways of making them better, stuff like that. So figure out how to do it, but be aware of the principles, because you're not going to just follow these principles as rules, because they're not rules, they're principles. So, yeah, so just think about it. Does it follow the spirit? Using variable names inside of your session is common because you're at the top level and you're trying to play with data. So sometimes you can't remember that data. So you just want to store that data to work with. So that is fine, right? If you need to name your data so that you can work with it, that's okay, right? The point is to understand where you should be using names and where you shouldn't be using names. So names for abstraction, potentially iffy. Names for referencing real instances of things that you're using in the thing, potentially okay. In my compiler, for instance, I generally, all my names appear at the top level, and I have a name per pass, and then a set of helper functions in the passes potentially are given small names. I'll show my compiler a little bit so you can see my interpretation of these principles in a particular use case. under the proviso that that's one use case.
I mean, we're probably some distance apart.
Yes. So I'm perhaps a pure extremist when it comes to certain things.
People who write APL code for money often use them.
Yes.
How do you do error handling in APL?
Do I show that or do I not show that? Do I want to show that or do I not? La 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 la. All right, I'll show a little bit. Okay, so basically you can manually signal errors with the signal system function, and you can signal things like a domain, a rank error using the number codes, and you can look at the documentation and find those. And then those can be trapped using quad trap if you're in a traditional traditional programming environment. I don't recommend you go with that. Instead, what you can do is you can trap error codes inside of defunds where this is what will be run here. However, I think in version, is 16 gone with dynamic trapping, or is it still lexical trapping? Have we fixed that?
Well, it's going to be dynamic. Well, yeah, I mean, I think the correct answer is dynamic.
Okay, so I think in 15 still there is what I consider one of the most serious bugs in defunds to have been allowed to survive across multiple versions of APL. And that would be that error trapping was lexically scoped rather than dynamic. And the whole point of error trapping is dynamic scope. Yeah. So, however, I think that has been fixed and won't be a problem. So what it means is that sometimes you won't capture errors that you expect to capture. And in those cases, you actually have to sort of create a new evaluation frame so that it pops into the appropriate place to get to your trapping. But that's just an ugly thing. This is what you should get out of it. Is this allows you to trap this error or multiple potential errors. So you can do the set of errors that you want to trap here, or things like that. Right. And then whatever you do, it does here and then returns out. Yeah.
I mean, you could show domain error is 11.
Yeah.
11 division by 0.
I didn't actually want to try to do anything because I was afraid of what would happen, but okay, fair enough. Yeah.
WS not found. Import something?
In what?
I'm just trying to copy that symbol.
Oh, not system, defunds. So copy defunds.
Oh, okay.
UTF-8 get. Yeah. Yeah, yeah. Yeah, defunds is the name of the workspace from which you're copying things. Yeah. Is anybody doing image processing? Okay. How's it going? Oh, sorry, I'm just like. Okay.
I don't understand why displaying a box in V displays 3 different lines since.
Oh, because there are new lines in there.
Ah.
Yeah. Yeah. So there are line endings and things like that.
It takes an argument. You just print it out.
I'm just doing math. It's
Cool.
easier to grok.
Cool, cool.
What's the argument for TFX in it?
The name of the namespace that you've compiled, getting ready. So, all right. So you're working on that now, aren't you? All right. Let me show you how to get up. So, for those of you who are working where you might be working with the graphics system, what you want to do is you want to be inside of your codefunds checkout, and you want to have loaded codefunds up, and then you'll have this codefunds workspace. Now, the codefunds workspace. Something like this, assuming that you're in the right path, it'll load based on your current path. And once you have that, you're going to need to configure it for your system. So there are a set of variables. There's the compiler you're going to use. So there are these 3 variables that you want to set. And AF prefix, if you guys just follow default install, should be user local on all platforms except for Windows, but we don't care about that on Windows. This is going to be probably AF CPU for most of you, unless you're brave. And then this is going to be the name of your compiler. So VSC on Windows, GCC on Linux, and Clang on Mac. Once you're there, you're going to, you need to create a sort of a codefunds object to work with so that you can access functionality. So I just do test codefunds fix, and I just create a namespace with the identity function. And when you run that, it should should compile it, run it, and create the right testing object for you. And then you can refer to codefunds functionality from that. And so your gfx init, you can then initialize your graphics functionality with that. And then I can do things like loading in an image. I think. So I have this. What is that? Oh no, Paint 3D, that's not what I wanted. Okay, so then I should be able to say load image. Okay, yeah, all right, so I will use, I'll load it as color, which is the default. So say image gets codefunds load image tick, like that. And if all goes well, you'll have your image, and it'll be loaded in as an RGB or something like this. And then you can display that image by whoops. Okay, there we go. And then you get your display, and you can start accessing graphics, playing with that, and so on, and so forth. Okay. You might have to hit escape or close multiple times. I'm still working on that funny little image loop, things like that. And I noticed that it might take 1 or 2 tries to initialize the system. Again, that appears to be some weird display stuff. So there might be a little roughness around the edges to work with, but yeah. And this is also how we did the life animation, but we used animate instead of display, and animate works a lot like the power operator. And Imager is one of these plotters that will allow you to display certain things. You've also got plotter, histogrammer, and I think those are the 2 other ones that we have. You probably shouldn't play with those until you've played around with a little more APLs so that you're used to how things work. Because they require you to provide input in the right format and things like that. But yeah, that's towards the end of your problem domains. That's what you'll play with to visualize your things. Okay. How's it going over here? Okay, great. And when you run it, it comes up? Yeah, cool. All right, excellent. Yeah.
So,
and we'll probably want to take a break in maybe, say, 15, 20 minutes, grab some coffee, 5-minute break, come back, stretch your legs, that kind of thing.
Trying to get random numbers.
Yes, random numbers.
Problem is
Yeah.
getting different random numbers.
All right, so remember your order of evaluation. Your random function is going to take whatever it's on the right and give you random stuff based on that. So if you want 7 random numbers, you have to give it 7 things on the right-hand side. So ask yourself, how many things are you giving it on the right-hand side? Which one is that? Yeah, sorry. So what does functional programming mean to me? So coming from the scheme background, I am not what I would call in the type theorist, pure functional programming domain. I currently don't have a use for monads, for instance, in the Haskell style or these kinds of things. Instead, functional programming to me means data flow. It means a way of thinking about the flow of the program without the use of unnecessary state change that is difficult to identify, or with a focus on functional composition and a focus on operating on values instead of references. So thinking of the world as values rather than thinking of it as references. Thinking of it as flow of state through a set of transforms as opposed to mutation. Yeah. Recursion, to me, so traditionally I would have said recursion is an important part of functional programming. I have now reached the point where I feel recursion is a useful but generally not necessary aspect of functional programming. So one of those things, it's like the if statement. I now feel that the if statement does not warrant the amount of attention that it's given. And I think that that should continue to be the case going forward based on how our architectures and systems are changing. So to me, functional programming, you have the scheme, you had the Haskell. Now I feel that it should be moving more towards a data flow as a concept, as opposed to some of the other things. And you'll see that when I show my compiler and my philosophies around it. It'll be directly obvious how I do that. And to me, my compiler very clearly expresses what I feel is my epitome of functional programming. But yeah, lots of data flow.
Also, you think it's a mistake to separate the language from the editor? I mean...
I think it's a mistake to use an editor as a concept. Yeah. So I think the editor itself has become a problem. But remind me to talk about that a little bit later, because that's he's heard me rant on that. But yes.
Can I need your help?
Cool.
Do you know what this is when I run it?
Yes. So that's because you haven't changed your variables, right? So you need to change compiler, AF prefix, and AF lib to be the appropriate things.
Okay.
So because right now it's trying to run Windows Visual Studio, and you need to change VSC to Clang.
I got it.
And then change AF lib to AF CPU, most likely. And then you can try to run that. Yeah.
Just trying to load that graph.
Yeah, so in that triple, you can assign a triple, or you can just refer to them individually without the parentheses in each variable. Just codefunds.compiler gets whatever, yeah.
Try to load that file.
You haven't put it as a string. UTF-8 get accepts a string as your path, and strings are single quotes.
Oh,
yeah.
Okay. And just out of curiosity, when I want to Google stuff, read it to APL.
Well, help.dialog.com.
Help.dialog.com.
Yes. Or Mastering Dialog APL. That's a book that covers most everything in it. If you need that, it's a little bit more industry, not as much fun. Yeah, yeah, it's only 800 pages, and it's a lot of frameworks, APIs, that kind of thing for business.com. DYALOG. Yes. Something simple. Yeah, you're in the middle of the debugging stack. You need to do a reset. Yeah, so don't forget about reset. If you get into a space where you're inside of the stack and things are not working the way they should, a reset will pop you back up the rest of the debugger and get you back into the right state. All right. How is the lonely middle road?
Hints on concatenate.
Catenate is join. It's joining two matrices together or two arrays together.
All right.
And if you read the docs, you'll find that on help.dialog.com. The language reference has the definition for catenate and examples. But what are you trying to catenate right now?
I'm trying to do exactly.
Which one?
This, concatenating these random languages.
Okay. So what's your input? You have T, right? Which is a matrix, right? So imagine how you would connect a matrix with a vector. Along which dimensions does it need to be connected? Which side? And play around with comma and first axis catenate. That's bar comma. Play around with those two. Those are the catenate. Bar comma. So it's the comma with the bar. Yeah. Play around with those two with different values and see what you get.
So I'm working on the
yes.
matching, right?
Cool.
So
cool.
I have this I have 0, 1, and then 2, 3, 4, 5. Sorry,
What did you do here?
This is counting. I'm trying to count the depth of the deepest nesting.
Wait,
right?
you
Am I
run
doing
that
that?
and that's what you get?
Yeah. So this gives.
What the? Whoa.
Quad equal gives you.
I didn't know key did that. Wait, we have a monadic key? Oh, wait, no. No, what? When did this happen?
No, that's been there from the start.
That's weird.
It's probably a mistake.
That's creepy.
Even Roger says it's probably a mistake.
So I probably shouldn't use this to solve this. Huh? Okay.
It's fine.
That's interesting.
It
Well-
uses it generates data, simply the indices.
Right. So
Yeah.
I'm trying. If I can just measure
Yeah.
I'm trying.
You're trying to measure how many.
How many you can go on the top before you get to the next one on the bottom,
Interesting.
Except
Yeah,
I don't know
you
how
could
to-
play around with that. Also, play around with some of the scalar primitives like equality. So play around with equals a little bit too.
Okay. Well,
Yeah.
equals will give me bools, right?
Yeah.
But bools aren't useful for detecting the depth, right? Or
Are they?
are they? Okay, I'll
Play around with it.
All right.
Both, I like the way you're going because that's not a way I would have thought about it. But that's interesting. Yeah. So we're doing with parentheses nesting depth.
I don't. Well, actually, okay.
Yeah,
so
it's interesting. I don't know. Yeah. Play with that. I like that way
There
of
must be
going.
some suggestivity at work.
Yeah. AF CPU is what I would recommend if you don't have a highly reliable GPU programming environment.
Okay.
Yeah. Yeah, that can cause some problems. Okay, what are we doing over here?
Just trying to download this.
Oh, it's already in the shared folder.
Oh, really?
Yeah. Here. Woo-hoo-hoo-hoo. No. Ha. So you missed the USB stick? Yeah. Also, we have a Lambda, the functional array channel on Slack will have a link to the shared folder, which you can download all this stuff from, including the installation guide. However, on the Mac, you're going to have to do some symlinking, most likely.
Okay.
So,
I can help you with that.
yeah, okay. So he's got some people. But you're going to need to make sure you have, is it Homebrew? Is that what it's called? Yeah. Installed, yeah. And your Xcode tools and X11, Xquarth, all that good stuff. Okay.
This one down. It was actually working fine. Now it returns 500s on the request.
So,
Hey, Morton, get a call into Bramley. Try APL is down. We crashed it.
So the site is up, but like if I do I over 10. The evaluation is broken and returns 500s.
I think what's happening is it's trying to restore your session or something. If you were
Ah.
to take your cookies,
Okay.
so it's your session that's broken rather than.
Okay, good.
My PNG is failing to load. I'm not quite sure.
Are you in the local directory that you can find it?
So here I'm in the directory.
Okay, so can you do a sh reset?
No, it's each time you type.
Oh, did you do your graphics in it?
Yeah. Change the compiler to C-line.
Yeah, you ran that, but you didn't. No, not save GFX. You need to do GFX init. So see that line there? Yeah, because that's
Yeah,
what
no,
it can't
the-
find the internal bindings
Okay.
necessary for.
Yeah, no, the save was just so I
Yeah.
didn't have to go through
Oh, okay.
that
Yeah,
step
cool.
again.
Yeah. Init, that one right there.
Yeah.
Yeah.
And then test is
Yeah.
just an arbitrary message file.
You didn't call it test. What did you call it when you fixed it? Oh, you did call it test. And it compiled. Oh, are you on Mac?
Yes.
Did you do all the symlinks?
Yeah. I got that example to run here. That was the Hello World thing.
All right, go back. Let's go run something in there. Back to the dialogue.
Okay.
Did you do the latest checkout of codefunds today?
Yep.
Problem is it can't find your file, so something is not. Do a reset and then go ahead and run util dot test the string identity, all lowercase. So single quote identity. Yeah. Yeah, see, your compiler is not able to load the right stuff, so it's not finding it. So let's go to this. Let's go into your build directory. It's building them, but it's not finding them. That's not good. So if we go back to the dialog. Yeah. Okay, so that's the problem basically. Is it's not able to load in that object file. So if you go, thank you. So if you go into your terminal, into the codefunds repo, and build, go into the build directory, and then do an otool-L on one of those dilibs, specifically your test clang one. Let's see what happens. Oh, you don't have
AF CUDA?
You don't. Yeah, you have to do AF CPU because it won't be able to load the CUDA libraries.
Okay.
Yeah.
So go back to this.
Yeah. Yeah. So that'll solve your problems most likely if you use AF CPU.
Okay.
Yeah, because the Macs don't have the CUDA stuff on them.
Is there good graphics drawing routines included with this to play around with stuff, or is that
So there's.
ambitious?
That's what the imager plotter and stuff. So what you can do is you can, if you do, are you doing image processing?
Basically, I have a crazy idea of.
Sure.
Do you know what dual contouring algorithm is? It's a way to find ISO surfaces.
Oh, okay. Yeah,
It maps really nicely to array processing, so I figured that might.
Yeah, so if you implement that in here, then what you can do is you can produce images as arrays.
What about 3D?
Yeah, so you can do 3D plots.
Okay.
3D plots, if you want, I can quickly implement a 3D surface plot for you.
We'll see. I'll
Okay,
start with
if
the
you
2D
get
case,
to the point where you think it's ready for 3D, it'll be a few lines in a commit, and I'll have a 3D surface plot up for you.
Well, I'll start with the 2D case just to
Okay,
simplify it.
cool. Yeah, I can add that in later today if you need it. Yeah, the graphics stuff is a new feature in this release of codefunds, so it's kind of yeah. All right. Let's see how we're doing. Working? Or are you just listening?
Just
Okay, that's cool. Yeah.
So in SSCP,
Yes.
the author modified power mod to Fibonacci mod to do quick Fibonacci.
Yeah.
Is that an example of suggestivity?
Yes, a little bit. Yeah. And in fact, you could try to play with implementing power mod here if you wanted to, and see what you get.
But there are no recursion or if statement. How?
Yes, there are. But see if you can do it without it. See if you can implement power mod without using if statements and recursion. If you need to, all right, I'm going to show you guys a little bit of how you use recursion and if statements in APL so that you can start playing around with more complex stuff. And really by that I mean using your old techniques so that I can go tell you they're wrong and to do it the right way. But let's just do a quick implementation of Factorial. Where are we? Here we are. Okay, so in Factorial we ask if the input is less than or equal to 0, then return 1, else take the argument, multiply it by the recursion of 1 less. And that should explain how recursion and branching works. So if you guys want to do stuff that uses recursion or branching, you can do it that way. Yes?
Question. Is APL
No, that is my goal. So APL has a strong history of executing on vector processing machines. It was one of the only language implementations available on some of the very large-scale vector machines in the 80s. Partly because nobody knew how to get other languages onto the vector machine, so APL mapped very well to those. APL itself right now primarily drives Wall Street, big oil, finance, insurance, medical, bio, and some other domains, startups, databases, that kind of thing. That's where it currently is used heavily in production.
That's where I came across it in databases.
Yeah.
This is an obscure thing.
It's been winning the fight on databases. Basically, in the domains where APL is used, they get really upset when people say, oh, look at all the SQL stuff I've got, because they scoff at it because SQL has been too slow for them for years. And APL significantly outperforms any of the popular databases that people are familiar with.
Right here, is there open source database?
There is, on Dialog, there's VecDB, and maybe, and later today, Morten will probably give us a demo of some database type stuff, working with tree.
I can see this being usable in time series databases and stuff like that.
That's exactly where it sees a very significant portion of its use. Now, my goal is twofold. Really, it's to scale up what people using APL can do, because the problems are getting to the size and the hardware is getting to the point where to handle large-scale data, you want really good parallel execution. So so I'm sort of scaling in two dimensions. I'm scaling on the performance side, where I want to get APL to really work efficiently on the GPU, on modern vector machines, because that's been a neglected problem for the past 20 years. And then the other one is to make it possible for people to scale their learning of programming, computing, and to these machines from the beginning all the way up. So I want to make sure that we have a language like this that we can teach to high schoolers, for instance. And actually, most of these, not to put you guys on the spot, but most of these problem domains were problems that high schoolers went through with almost no guidance. Well, a lot of my guidance, but they wrote the code themselves in a 2-week, 12-hour session with no computing background at all. They did these domains. So you as computer scientists have it a lot harder, because you have to unlearn a bunch of things before you can learn it. But that's what a lot of these problem domains were oriented towards. Anybody who's seen the live stream will be familiar with this, but let's just look at some code that I've been working on. And this is how I view APL. I should preface it that, as Morten says, this is not the kind of code that most people would be writing, but it is a highly optimized form of coding expression that I find extremely useful in my own work. So I can explain why in detail, and I tried to on the Hacker News discussion explain it, but I can explain in detail why I find this to be a particularly useful way of writing code. However, it is not what I would call the average Joe code that you'll find in most APL communities. So yes, and then I think we should see Morten's code to see perhaps a decompression. So yeah, and Morten will show something more akin to, I think, what the normal APL programmer thinks about code. So if you guys will have noticed in your checkout, this is the Codefunds compiler. So what we have is a set of files, A through U, .cd. That's the compiler proper. You have tests, some other stuff, but that's where the compiler rests. I believe the total line count is maybe around 1,500 lines or something like that, including the runtime. I didn't bring my t-shirt with me today, but I have a previous version of the compiler that fits on my t-shirt. The start here should immediately throw up lots of red flags for most people in their best practices. Why am I using single letters that apparently have no significant meaning? And the reason is that this is an homage, or a form of self-documentation that points to what you're about to see. So it's my "there be dragons" here note, because famous array programmer Arthur Whitney was kind of infamous for doing this thing in his code. And because I'm using a style of C code in the runtime that very closely mimics some of Arthur's conventions, I put this here to let any APL programmer who sees this sort of know ahead of time, hey, you might want to prepare yourself for this class of programming rather than other stuff. So the way the compiler is designed is to fit onto 2 pages at a time on the system.
Quick question.
Yes?
What does it compile?
All right, so it is a compiler written in APL defunds, compiling APL code defunds, which is a slight extension, but right now it's basically defunds, the language you guys are learning, to C++ linking into ArrayFire for the CPU, OpenCL, and CUDA. And it is designed to execute, the compiler itself to execute in parallel on the GPU. So rather than...
The compiler itself executes on GPU.
So it's not quite self-hosting yet, but that would be the eventual goal. So executing of the compiler itself on the GPU. So rather than a compiler that runs on the CPU that generates GPU code, we've now got a compiler that executes on the GPU itself. So this is the starting point, and this is where we begin with the overall style. So on the left, you have the regular... This is A and B. And this is the public interface here. And this is the back-end and front-end linkages. So you've got your back-end C compiler stuff going through. And then you have below that, if I stop getting email, you have your AST description. And this allows you to sort of understand the overall structure of how it works as far as our data types. So we're still working with arrays. However, we're going to be using a linearized representation of ASTs, known as the quad XML derived format. And this is how I sort of document what I'm working with. So inside of my compiler, there will be these types of nodes and those fields. So we have a set of 11 fields, DTKNR, SGV, YE, which is the depth, type, kind, name, reference, scope, guard level, values, types, inferred, environments, and live variables at that point. And every node will have those fields throughout the compiler. Early on in the compiler, there won't be as many fields. Later on in the compiler, you will have all of these fields. And then every node will have a type, which is either A to Z, something in A through Z. And then, remember that we're talking about macro level views, right? So rather than doing traditional work, I have a set of accessors for nodes and a set of accessors for fields. And this is where the naming conventions start to come in. So I care a lot about names and making sure that names are not used to do things that structure should be used to do, and they can instead be leveraged to communicate within the domain of compiler writing. So for me, that means I'm trying to write so that my variable names stay within the domain of compiler writer concepts. And that would mean that we have these nodes where ZM, YM, any of these are going to be taking an AST as the right argument and returning a Boolean mask over that AST, identifying all of the nodes of that type. The AS and so on accessors are going to use that mask to extract out the set of nodes of that type inside of the AST. The field getters, when given an AST, are going to get out that particular field for every node in the AST. So you can think of these sort of like column accessors and row accessors, or record identifiers and field getters inside of a database or something like this. And so that's sort of where we're framing this whole situation. So we've defined our exit, we've defined in our minds, our incoming point of view, which is going to be these things. And everywhere, these names are valid, right? This is a flat namespace, so I only use those single letter names almost always in this form when they're in the right mental scope. So then, what's the first thing you do when you have to go in and compile something? Well, you have to parse it. So here's the parser. And notice again, 2 pages, all the code on one screen. This is important to me. So I work to make sure that all of my code fits on the screen at the same time for any given space of the compiler. And I work to make sure that I don't have to scroll. And so you'll see why I don't feel that editors are a good idea. Structured editing is actually interesting because structure editing is another form of eliminating scrolling. If you have folding text editors, that kind of thing. The folds are ways of getting rid of scrolling, or that kind of thing. This is just an extreme way of doing that. And you'll notice there is zero syntax highlighting. So this style of programming is, in a way, a very aesthetical as well as aesthetic style of programming, because what I'm doing intentionally is stripping out as many of the tooling assists and aids that I get from other environments that make my life easier, so that I am only allowed to simplify my life by simplifying my code. That's the goal, is to use my tools in the inverse manner, make it more difficult to leverage tooling so that I can only really leverage language level simplifications and architectural level simplifications. Because once you reach a point where your code is complex enough, then you can't just play little fiddly tricks inside of a piece to make your code simpler. You have to start making broad sweeping architectural changes in order to simplify the code. And so everything here is pushing me to have to do that, because I don't have all of the tooling support that you might use to get away with slightly more complex code. So I'm doing everything I can to only allow me to be able to think about the code in this one way, so I have to make it as simple as possible. And so this is a peg grammar. So the implementation for peg parsing is up there in the underscores. You guys can see and use that if you want. So that's a peg parser combinator library for peg grammars. And on the left-hand side, you can see, did you have a, oh, okay. On the left-hand side, you can see the terminals of the parser. And then on the right-hand side are the non-terminals for parsing the system, and they just use the combinators over here. Interestingly enough, APL is a slightly ambiguous syntax, and so we have to do type inference while we're parsing. So this compiler will identify which variable references are data types and which variable references are function types, and infers that through here. It also supports recursion, forward references, and all of that other stuff. Because it needs to do type inference, it also has to be aware of all of that other pieces. So it has to be able to do forward referencing and things like that. Now, here's the compiler. So the compiler fits on 2 pages of text, 12-point font. Yes? But it's not actually scrolling. TT is the bottom end of it. It is pushing the limit a little bit over here. So I'm working on simplifying that. I actually really need to code golf this. This is the inline pass. So this code right here inlines functions. And it's a little bit long. Way too long, actually. That's probably double the size of any of the other compiler passes. MR could probably also be simplified. Yeah, so it's way too long. So we'll work on simplifying that. But yeah, so the point is, when you think about your compiler, I find it much easier to write compilers if I can see the entire compiler all at once. Because now I'm able to reason about every aspect of the compiler and see it at one go. So you were asking about code duplication. One of the reasons code duplication isn't a problem is because I can see all of my code.
Well, I'm more just, if I have to fix a bug in one piece and I forget that it's duplicated it somewhere else, that's my biggest concern. I don't better.
Yeah, well, but you can see all the instances of your duplication at one go.
So you wouldn't put another instance in another file?
Probably not.
Okay.
If I had to start crossing so many different file boundaries, I might put a function there to separate that out. But oftentimes, I'm in separate spaces, so there is no code sharing there, because they're very separate, very different pieces. So there are a few things where they are common, and in those cases, I might have these helpers. So these are a set of helpers where I need to do things, and these might be used elsewhere. Now, there's another subtlety to this code which you guys might not have seen, and that is that none of these is a line of normal expression code. Every single line on here is a function definition, because this is written in the trains point free style. So these variable names that you're seeing here, like this one up here, D is not a reference to a piece of data. D is the function, the field getter, accessor. And so this whole line is the generation of a single function by function composition. And so the whole compiler is just one giant long data flow graph and implemented without branching, recursion, looping, any of that stuff. It's just function composition put together like this. So if you want to see a little bit more about how the syntax works, you can, well, let's do that. Let's take.
Was that style chosen for the ease of implementation on a GPU?
Yes, partly. Partly because I've actually found it easier to work with in general. So let's do boxing on trains tree. Yes. Okay. So that's how you parse that line. Where the D is where you see that alpha alpha get stuff. Alpha alpha squad transpose. That's the expansion of the D getter. So we can replace that with D anywhere you see it. So this is a function definition, but the way it's composed together is using these function trains, which have atops and forks. And you can play with this if you want in your own code. You can read about trains in the dialog documentation and play with using it. What I have found is that if I restrict myself to in a disciplined manner to only stay in the trains notation here, then what I can do is I can eliminate another abstraction level. So I've eliminated the barrier of defining functions and defining values. And instead, all I'm doing is defining functions. And so now when I read my code, I can read it almost as if I'm reading expressions. I'm no longer reading a separate set of things. I'm just reading expressions. And so it becomes as easy to read as regular expressions are to read. And so this is where we compose it all together. So we start over here, and we run each compiler pass until we get to the end. And it's flattening it out and working on it. And I've got a paper that you can read that shows some of the fundamental data types or data structures that are used in here, such as path matrices, stuff like that.
Where does RN use?
What RN does is it registers the R field. So it registers.
There, where is it used?
It's the first pass of the compiler. So that's the entry point into the compiler. And then there's a 2-letter code for every other compiler pass, and the 3 letters in there are prefixed by the 2-letter code to which they belong.
Are these each full passes over the ASD?
Yes.
So, just general question, do you have a garbage collector, or is it just basically based off of?
The code defunds language can be implemented using stack-based allocation. And so like the C++'s, I don't know, they call it first. Yeah, something similar to that.
Okay, so I mean, like if you had large binary blobs of data, that would...
It's stored in the heap, and it's stored in the heap and managed, visibility is managed by the stack. And so at the end of a stack frame, those are freed and collected. So exactly like C++ vector types might be used, or any other object type might be used that's stack allocated in
I mean, imagine
C++.
this stuff is stupidly fast because you have no control flowing, no recursion, so you're basically...
Potentially. Asymptotically, some of these are slightly more asymptotically complex than their brethren. So some linear passes might be n log n, but that's because we have to do it on the GPU in parallel. And there are linear dependencies that have to be dealt with in certain ways.
Are these, so each function defines a pass with the AST, but when it actually executes, are those used into like one single pass?
Not right now. They could potentially be. It's an open question how much that fusion would gain us. So that's future work. And also, interestingly enough, it's possible to automatically derive the asymptotic complexity of this compiler.
How?
Well, if you have a function that's big O n, and you have another function that's big O n, and you want to run after the other, what's the complexity? 2n. If it's together, so you have a function that's composed with another function that runs it multiplying, it's n squared or something like that, or n to the n or something like this, right? I only have that kind of composition in this compiler. And the asymptotic complexity of every primitive is known.
So for the HCI part of this, I'm going to take you away.
No.
For the HCI part of this, how long did it take you to be able to sort of look at a source file like this and really just be very confident?
That's a good question. I don't have a specific answer for you, but I will say that I struggled a lot getting some of this implemented in a more traditional style and eventually went to this style out of desperation in some sense. It was easier. I was able to solve the problems a lot better. Yeah. Now, it did take many, many iterations to finally say, oh, this is really what's working for me. So I started with documentation that was 500 plus pages for the parser to try to deal with APL's notation and come up with a very, very specific semantics or behavior for everything and really map it out down to the token level. And it was like, nah, didn't work. So the smaller it got, the easier it was to work with. I started using defunds. Okay, that was easier, but then recursion got in the way because there was certain stuff in there. Then I realized with the path matrices, which we can demo a little bit later, that I was able to do all of that with just this plain stuff. And then it became much easier to work with ASTs, and much easier to process things. And so then I was able to write this stuff fairly easily.
So what about the criticism that, I've heard other people talk about, J, Apl, white noise, and that other languages are sort of more verbose, lend themselves much more readily to other people being able to sort of take up your code.
Right, right. So there's a few questions in there that you have to unpack. Yeah. One, what's the definition of readability? What do you care about?
So I like it.
Yeah, but there's a few things. One is, do you want your people coming in to have to learn 10,000 lines of code or 100 lines of code? Do you want to be able to read a single line of code in a second, or are you okay taking an hour to read a line of code? Then you have, do you want a single piece of code to be easy to read, or do you want the whole code base as a whole to be easy to read? So there are trade-offs there. Certain compilers like Clang attempt to make single small snippets of code easy to read. But understanding the whole architecture of Clang requires extra documentation. Understanding the dependencies and how code flows through the system and all of the dependencies that are there is very complex, even though you could read a single piece and say, oh yeah, that's easy. Here, it's the opposite. One line might take you a little bit to really see what you're getting in, but seeing how it all flows together and fits together is much easier.
Is there something you said also for not having novices come to this and break it? Or in other words, the time that's spent sort of learning right?
Yeah, yeah. Well, yeah, so I'm of the mind that don't fool yourself into thinking you know how a code base works.
Sure.
So my view on readability would be, how much are you willing to bet that you make a change to that code and it won't break? That's my definition of readability. Less than, I think I know what this is doing. I kind of have the idea, but until I run it and compile it and see what happens, I won't really know. I'm willing to bet much more that a change here, I'll be able to figure out whether it's going to break or not, than in other systems where I don't really have the ability to see the whole thing and understand the whole thing. And that's where I think the big difference is people focus on readability at the micro level rather than readability at the macro level. And one of my goals, one of the things that comes out of working in this style is that I'm much more willing to expect certain things to work. And if they break, I really know why, as opposed to complex systems which have emergent behaviors that are very difficult to debug sometimes.
So related to that, so for example, Haskell has this loose saying that if you compile it, it works.
Yeah.
Is the same thing similar to apply here?
Similar. The response would be, don't write broken code. Now, it's funny because most people think that's impossible. I might weaken the statement a little bit, but it's much easier to imagine 2 pages of code that you're convinced are not broken than 500 or 5,000 lines of code that are not broken.
Right. And then for the Haskell side of it, just because it type checks doesn't mean it's correct.
Yeah. So typing is an interesting one, because I actually won a previous version of this compiler to check for correctness. I was following a formal semantics process where I annotated the pre and post conditions of my various stuff and determined what were the correct behaviors to find a type for them, basically. Now the problem is that I discovered that to type one of those lines in any way that was useful to me, beyond just, oh, it's an int or a float, okay, you've got a type error. Something useful like, oh, you're not balancing your tree, or oh, you're not tracking these things. To write those types, it was like 7 lines above, 7 lines below, 1 line of APL. At that point, having the ability to do that it was no longer useful, because it was easier to reason about the code directly than it was to use the types to reason about the code. And so I find that to be a good metric. If I can push so that types are no longer useful for reasoning about my code, then I think my code is pretty simple. That's a sort of a metric I play with. And if I feel that I could use a type system to track what's happening in my code, then maybe I should try to simplify the code a little bit.
So if you give something an array that's supposed to work on an int, for example, does it blow up on you, or is that?
This?
Yes.
I'll get errors if you get you can get these sort of silly type errors. Yeah, that won't get caught statically. They'll blow up at runtime.
Oh, they do blow up at runtime.
Yeah.
Okay.
The thing is those are easy to find, easy to fix. It's the more complex errors that are harder to find, harder to fix, and that you really want a type system for. Everyone can track down I'm using an int, a character instead of an int bugs. Those are easy to track through a program. I forgot about an invariant somewhere in my code 7 passes up, and I'm dropping an AST somewhere that it shouldn't be because I'm assuming something above. Those are invariants that you want a type system for. So that's why I'm much more friendly to dependent types than, say, regular C types or something like this. Because your runtime checking is usually good enough to find the easy stuff. The harder stuff is more. So yeah, and then after this, we just go to a flat space where I dispatch on, the result is a flat space where I can just in parallel run generators on this whole thing and do it. Now, an interesting situation is what do you do when you have to work with C code and you're used to looking at code that's that dense? And believe it or not, this is actually a problem. If you have to jump back and forth between code that's airy and code that's very packed, it can be quite difficult. So what I do, I want to find a simple, let's do more canonical stuff. There we go. Is I write in a very dense C style. Also called the Whitney C style. But I work in a very dense style that mimics the density of APL so that I can reason about it at sort of the same level. And I use a style that mimics APL structures. So that when I'm jumping back and forth between APL and C, I don't bust my mind. Now this might not be indicated and recommended for people to do everywhere in their C code, but it does have benefits. But yeah, so this is one approach, my interpretation of things, but I think Morten has some fun demos that we might run through. And of course, you guys should continue working on your problem sets, but I figured I'd show you some code that's a little bit more complicated than what you're working on right there, and see how it works.
What is this?
That's just a sort of mathematical convention. I'm saying this is equivalent to that, which is equivalent to that.
I don't get it. Isn't this like the W combinator?
That's commute. That smiley says commute, so it's a selfie.
Yeah.
Oh, you guys didn't know we had selfies in APL, did you? Here, I'll show you what the selfies are. So, we have commute, right? So we can do 3 commute 5, right? Minus 3 minus commute 5 flips it around, flips the arguments, right? But we can also apply it to itself, which is a selfie, which turns out to be really interesting because, for example, we can take 20 random values like so, then we can apply the find function to itself, and what do we get? So there are lots of little selfies that you can do inside of APL that turn out to be very interesting little computations. So does that make sense?
Oh, I see.
Yes.
Maybe you should put it on 2 lines.
fresh and I had an hour to go and sit in a dark room, I could do the bracket thing.
Yeah.
I don't want to try.
You shouldn't. The brackets is a tricky problem, so you shouldn't feel bad about.
I'm not going to offer to live coding.
But it's a tricky problem. But it's one we played with at the Iverson College recently,
I think
which
it
is why I
is.
wanted to.
I think there is a way to do it with some inner products and some outer products.
Yeah. So what you're looking for is ways to find overlaps of depths. So if one of the brackets, basically you need to look at your boundaries. So if one of your boundary cases for one of them overlaps a boundary for another, you're in trouble. So what you have to do is look for, because you've got those depths, and those depths represent a certain sort of greater than or less than thing. So if one of them starts here and then suddenly shifts in size and value, you have to flag an error. And you don't have to pinpoint the exact place where the error occurred. All you have to do is identify that something happened. So for example, finding a mismatch parenthesis is just looking at the end tail. And then you have to scale that up a little bit. So yeah. It's a little bit tricky. But it's all right to skip that and just try to parse, try to use parser combinators, or it's all right to try to run the parser or do whatever. If you feel tired and you need to get back to it, you might try playing with some other stuff, come back to it so you can sort of get a little bit more exposure, and you're not just spinning your wheels on a single problem.
You need to identify all the transitions and then look at what the other level is. But you need to find them matching. Yeah, they might not be next to each other.
So I now have a vector of vectors for all my strings.
Nice. Excellent.
I want to
Personally, I would have processed that with UTF-8 first to get the text values instead of the byte values, but yeah.
I thought I had to convert it to that. I can always convert it back.
Because you can work off the text. You don't have to just work off the bytes. You can work off the characters if you want.
Okay. Trivial.
Yeah.
I wanted to drop
Yeah.
the new line, so like everything's prefixed with 10.
Yeah.
All right.
And you have 10 at the beginning of every line.
Exactly. So
Right.
I thought I should be able to use this drop.
Right. That's the
It's
right
a
way to
vector
go.
of vector.
Yeah.
But am I invoking this wrong?
Yeah. So there's a rank error because that's expecting a vector of rank 2, but that's a vector, so its rank is 1. It's just got a depth of 2. So what you actually have to do is go in on the depth, which is what each will help you do. So what you really want to do is you want to drop 1 off of each element in the vector. Yeah, rather than dropping 1 off of. Now there are other ways to do that, but you can.
I thought the 0 in the front allowed me to basically go into each vector and drop off.
No. So the way that drop would have to work is if I have a 3x3 array, then I can do a 0, 1 drop. But the restriction is that the number of elements I have here must match the rank or the shape. So I can't drop 2 things from something that only has 1 shape, because the resulting shape is basically 3x3 minus 0, 1.
A vector of vectors is not equivalent to 2 dimensions. Okay. I mean, some languages, they pretty much are, right?
Right.
In APL, they are very different.
Okay.
Right. You can convert back and forth between them. So like this guy, you can convert by dropping the monadic split. And so what that does is it takes one of the dimensions and converts it to depth.
Oh, that's interesting.
And you can also take, which converts one of the depths to an added dimension.
That doesn't help me because it's variable length string. Right.
Yeah.
So you did need to do it all.
Yeah.
So how does each work?
It's map. For the moment, just think of it as map.
It's map.
For the moment, just think of it as map, yeah.
And the APL primitives are really divided into 2 very, very different groups. There's the scalar functions, where the map is implicit like plus functions. Something like you have to wait to
Ooh, hey, that's not bad. Looks good.
It looks like sometimes
each line goes back up.
They are not scalar.
And that doesn't make sense to me.
Oh, really? Let's see what you have. So you're running it? That's okay, so you run it. What does your garbage function look like? All right, so you're taking the count of weird, reshaping it. Why are you reshaping the count? Oh, because you want to. Oh, so.
To go back to the size.
An interesting way to do that, yeah, okay. So you get one less to shape it along that, right. Catenate on the next one, then rotate along randomized, and then you negate the whole oh no, that's in the front, okay.
Yeah, I negate to.
So.
Yeah, so I add the word characters at the bottom, and then I rotate.
Yeah.
So
that's the right idea.
Top.
That's the right idea. But you're doing only by 0 and 1.
Yes.
Because you're getting your range on 0 and 1. So you get 0 and 1 if you negate. Yeah, so they're actually, it's just what's happening is sometimes they don't drop.
Yeah.
So sometimes they drop by 0.
Feels like sometimes it jump up.
That's a visual trick. So if you either made them jump, yeah, so that's just a visual trick. Yeah, it's a trick of the mind, because when some of them stop, it changes the perspective. Like when you see a tire on the highway and it spins one direction and suddenly it spins the other direction. Yeah. But yeah, that's pretty close to that's the right general idea. Yeah. Yeah. Excellent. Very nice. Who else is working on Enter the Matrix? How are you doing on it?
I'm just thinking about the next step.
Okay. Okay. If you think you're about ready, because I think he's basically gone through Enter the Matrix. So if you're pretty close when you get finished with yours, or you feel like you're good, I can show you our solution.
Okay.
You can see what it looks like. Okay.
I think we have until about 5. There's a keynote in here at 5:30. So we can't run until.
It can't run until 6:30.
Until 6:30.
Okay.
So we have an hour and a bit.
Okay.
And then we should try and wind up.
All right. Cool.
I'm going to take a little break and try and double check that so we don't get thrown out.
Yes. That'd be good. And actually, if you guys want to take a 5-minute break, just grab some coffee or something like that. That might be a good idea too. How are you guys in the middle doing? Yeah? You making any progress?
Yeah.
Right, cool. Anything you want. So think about how you might want to parse it. We're going to do a little bit of playing with different types of data structures and nested structures when Morten gets back.
Okay.
So yeah, I think I'll have him show his XML demo.
Cool.
Yeah. I need to find some soda.
And that's a throwback to the old mainframe days, where originally we used teletype, right? So we always had the log on the paper, and then the strings arrived when people really missed having the log of what they did in the previous session. So we still have that, and it's actually very useful.
Yes, I like the logs. Yeah, so you guys have seen some stuff, you worked on some problems. I recommend if you continue working on this, you read the paper on the tree processing, you read, well, you just keep reading. Yeah, pretty much. The domains have a lot of fun stuff that you can play with on them. And you can, but I don't think we have time to go into any more detail on it in the official point of view. I'm going to be here the rest of today and probably maybe a little bit of tomorrow. So I'd love to talk with you guys offline about any questions you had. I'd like to say go forth and make disciples of all programmers, but I don't know if we're quite there yet. But I wanted to see what you guys were thinking, where you are in your code, what was difficult, what was easy, what are you thinking? I also, we didn't really get enough time to discuss how you integrate this into a wider framework. So I think I would like to put some papers out that you can read about that. I mentioned it a little bit earlier, but there's this concept of direct development, which is a style of agile-ish kind of programming where the development loop has become a dot instead of a cycle. And in that, your customers are working with you on the code. And the code might look a little bit more like what Morten has shown you. But basically, the idea is when a customer has a problem, they come to you, they show you the problem, and then you work together immediately to fix the problem. There is no separation. Maybe it goes through QA checks that are automated as you go through. But the idea is if you can write your code in the right way, specifically variable name, if you can make sure your variable names make sense to your users rather than to other programmers, then the users can look through the code and oftentimes they won't see the symbols. They'll just see what they can read and they'll be able to sort of track the flow of the values through and determine whether or not this looks like something they need. And you can play different things like mapping the and reduction onto a word called all or any, if that's part of what they think of. So for example, if part of the question is doing queries on data, and one of the things they want to know is, are all these things true? Then that all word might be one of your user domain things. And so instead of writing and / you would write all, because that's now in the user domain space, and you want to have a word for that. But the idea is that you keep your names as much as possible into the user space, do pair programming with the users on parts of your code. Some parts they're not going to touch, but parts that the consumer cares about, the parts that they're actually working with, and that they're in control of the logic for, things like this. Rather than having a separate spec that then has to go through design and implementation and analysis and this sort of stuff, why not just have your code be the spec and let them work directly on the code? And this has been used successfully in various pieces. And you can use that to integrate some of these ideas into wider workflows. And then also the Codefunds compiler, you can play around with that in your own time as well. There's some instructions online, and I'm happy to walk you through how to use it. The idea is the code that you're writing right now, this style, the idea of the Codefunds compiler is to make it possible for you to play around in dialog and then fix that function using namespace and then get a version that will execute on the GPU or in a compiled version and play with the performance of it, as well as give you the ability to do other things like that. Other than that, I don't think I have anything more to mention, but I'd like to hear from you guys what you're thinking of. I know you're probably all quite brain dead by now at this point, but yeah.
What's the community like for this? Like, as far as tools and support from other developers?
Yeah. Well, so it's interesting. There's an active, but I would say kind of hidden community because a lot of people are working behind NDAs when they're working with this stuff. So there's a lot of passion for the language, but oftentimes you're not going to get a lot of libraries or other things out of it. But also, like I said before, there's this tendency not to rely as heavily on tooling. There is a lot of tooling out there, but tooling is used differently. The tooling is at the interface boundaries from the language to the rest of the world, where you're like interfacing with .NET, ODB drivers, ODBC? Yeah, ODBC drivers, database type stuff, networking. Those are all, and all those are often baked into the interpreter or baked into the implementation that you're using. So there's been a lot of debate over the years, I think, on should we have a standard library, should it be easily accessible, and there have been efforts to provide that. But in my opinion, one of the biggest strengths of APL is having the idioms supplant most of your library needs. You'll still need libraries here and there, but for the most part, the idioms go a huge way in removing the need to have a set of libraries. So that's a set of tooling that you don't rely on as much. And then so on and so forth. So one of the biggest problems with APL perhaps is that it makes you too productive. And so you end up programming alone.
Well, I mean, it's like, I was trying to do some of this stuff, and
yeah.
normally I go look at examples of other code, figure out how other people are doing things and what's available to me. Does that exist for APL?
The Fin APL idiom library is one of the classic sources for that. A lot of people rely heavily on that. You can go to Project Euler and see how people are solving the Project Euler problems with J and other things like that. There's the APL wiki. There's the APL news group. Dialog has a forum that you can use to discuss problems. Okay, yeah, so Stack Exchange. I think Dialog runs a North American training workshop type thing.
We've decided not to do those anymore. It's all online.
Oh, okay, webinars.
We're doing monthly webinars now.
Right. And I'm also considering starting a weekly live APL lunch series or something where I just do live coding sessions with people who have questions and go over APL, that kind of thing. So there is the community, but the community is different, I think, partly because the language is different. So it's not the same as like the Python community. But I think part of that is just the language is very different. So it leads to, and there's a lot of old guys who have been doing this for 40 years.
They have very old libraries.
Yeah.
That makes them even less interested in developing new libraries.
Yeah.
I mean, there's really a new generation of users coming out now. I mean, the interest in APL, I think, is dramatically increasing. The interest in parallel programming, functional programming, is making APL, although it's nearly 51 years old now, looking much more sane than it ever has.
Yeah. So I think you had a question?
Yeah, could you talk about the database integration of using APL instead of SQL?
Yeah, so one of the big advantages to working with the array language is that you're able to do in-memory column store databases very easily. And Dialog has a lot of facilities for storing component files or files onto disk.
Yeah, you can memory map any variable can be memory mapped to an external file.
So you don't have to just store your data in a workspace. If you've got your database in these memory map files, they're out stored on, you can do duplication, you can do that kind of stuff. You've got file servers.
One of the problems is there's not that many libraries because it's so easy to write your own custom object or column store.
Yeah.
That people just build them in a few minutes, right? So you have, basically, you have the memory mapping, you also have a component file storage mechanism. Any APL array and write any number of files.
And then APL is just your query language. So APL very easily maps to things like your, what is it called? What algebra? The underlying relational algebra. It very easily maps to the relational algebra. So if you're writing your queries and you can write a relational algebra expression for it, you can just as easily write an APL expression for it. And you just learn a few tricks about how to best orient your data, and because of the vectorized operations, because of the high-level optimizations you can do about what data you actually need, and because there aren't as many abstractions between you and your data, you can go extremely quickly. And that's where they really shine.
What's the difference between APL and J?
APL was sort of the first iteration of things. Iverson then, my understanding is, wanted to rationalize APL into another set, but this was done at a time before Unicode had really become the thing. So one of the things he did was he took out the symbols and he rationalized APL sort of away from the APL2 stuff and tried to sort of improve on what he felt was the appropriate way of doing APL. And I strongly believe that the choice to go back to ASCII was an incorrect one. But the rationalizations I actually like a lot, and fortunately Dialog's been doing a lot to get the J features into Dialog APL.
That was going to be my question. I want to riff a little bit on that. So, is there any feature in Dialog APL that takes you from a sort of verbose definition to a tacit? As you're learning how to do this stuff, right? I mean, we saw a lot of those tacit definitions in your source.
Yeah.
Right? But is there a feature in Dialog that does that?
You mean like an auto conversion?
Yeah, pretty much.
No, no. Part of that is because it's an artistic process. It's not a mechanical one. So.
Why would you want that?
No, I mean, I sort of
it to get a little bit more performance out of the interpreter.
Okay.
And then if you have to debug the code, you run the inverse unique.
No, that's exactly the word. That's exactly the word that was going. That's exactly the word that I was going for.
Yeah.
That they also, in their sort of propaganda sheet, their documentation, talk about using that for program transformation, right? So you can create a definition, and because there is a way to convert it into a tacit definition, you can get an inverse on it.
Yeah.
We don't have that. I mean, we have, Roger Dewey, who's the main J guru at the moment. He works 4 days a week for us and 1 day a week on J. So super.
Yeah.
Key, function names,
Rank.
tally, all these things.
Tile.
Really good, we felt were really good ideas that went into J that didn't conflict with anything in APL, finding their way into APL.
Now, regarding the debugging of trains, I'm actively interested in making that a better process. So in the compiler, I use a poor man's side-effecting printf, basically. It's the identity function that does a printf. But I'm expanding that concept into a full-blown sort of IDE visualization type thing, which you're seeing starts of that with being able to visualize data, animate it, things like that. And I plan to improve that as it goes forward. So in my view, the need to, say, expand out your code a little bit or go back and forth between the representations, I want that need to shrink significantly. So I want you to be able to debug trains as easily as, or really remove the distinction between debugging and exploration in your code. So I'm actively working to make that easier so that trains become a very, very simple tool to use for people. So, let's see, yeah.
Given that the dialog program is an interpreter, when you compile your code to GPU, do you manage to turn it completely into a fully on-GPU process where there's only data transmitted at the beginning and only data coming out at the end? Or
Yes. So it will never go back and forth in the middle if you don't make it do that. Branching, for example, I don't do on the GPU. So if you use an if statement, for example, inside of a nested computation, that will really mess with your GPU stuff. So if statements need to be on the outside of your GPU computation, and then those will run on the CPU, and they'll have to do a transfer there to do the test, because your if statements are running on the CPU. Otherwise, once you get from dialog into the function, it goes all the way through, and it's disabled right now, but there's caching functionality as well, which allows you to get back into the interpreter, do more stuff there, and then go back to the GPU side while having the data remain on the GPU side cached if you don't need to use it on the interpreter, but you're doing something else and you want to go back to that so that you can keep the data cache and keep it on the GPU for longer. And so you can, the goal is to try to keep it as much on the GPU as possible. So I do try to go as much on that. Yes?
So I noticed when I was doing, working through problems that it feels similar to like MATLAB in a way. Like I took an image processing class in school,
Right.
Or Julia or whatever.
Right.
And it's like if you basically want to work on the matrices and do all your operations over the whole matrix to get the parallel processing stuff.
Right.
Was MATLAB sort of influenced by APL? Or what is the?
Yeah.
Okay.
I think Mathematica, MATLAB, Julia as well.
Yeah.
But it's this semantics versus syntax discussion, though. I mean, in MATLAB, a column vector and a row vector have different functions to do the same operation on them. And in Julia as well, they've done a whole bunch of things where you've lost the generality of APL.
They've gone the library approach, basically.
Might well make the language more popular because a lot of the problems that 80-90% of the people are trying to solve, MATLAB feels more directly applicable. I mean, that's why they are well-designed products from that perspective.
Yeah.
But
Yeah. So I think the trade-off is MATLAB. If you can find the library calls, then you get call. Okay, seems to work. With APL, it's much more. You can scale your problems to more specialized domains, or you can explore different approaches, I think, in a more effective manner. So I think it's a better problem-solving tool. MATLAB, I think, is very highly focused on solving pre-existing problems. And I like the fact that APL, I think, is very good for solving unknown problems. And really, I never feel a need to go to MATLAB from APL, whereas I feel like there could be needs to go to APL from MATLAB because of the language is just not as nice. The libraries are very extensive.
Julia is nice though, right? I mean, it's much different.
I think the Julia guys are trying to do some really cool stuff. I obviously have a very aesthetic sense of what array programming ought to look like, and I feel like that's important because I think aesthetics are actually very important in programming. And I think that makes a big difference in how you see the world, how you see problems. So that's a big thing that I think people miss. For example, I came to APL because I tried to implement APL in Scheme. And I was like, yeah, I could do all the semantics. Yeah, it looks all great, but that's not APL. It doesn't feel right. When I work with it, I don't get the same ability to manipulate data in the same way.
I mean, NumPy is also.
Yeah, NumPy is another thing.
Also an APL implementation. Jim Rubuting says APL doesn't like
Yeah.
with parentheses and stuff.
Yeah. And my fundamental claim is that the visual aspects are critical to making a good array language, because you're writing a good math notation, basically. You're trying to find a good way of doing the same type of problems that people develop math notation for. And there's a reason, maybe not good or bad reasons, but there's some reasons why math notation looks the way it does over time, right? And that's a highly optimized notation for expert mathematicians and physicists and scientists to solve real-world problems. It didn't get that way because people think that notation just is, willy-nilly. There's a reason they don't use M expressions or S expressions in that domain. They knew about those things. They could have used computer code-esque stuff, and in fact, they did. Back in the day, you had to write English to do your math. But there's a reason they've switched over to using these other notational conventions in math because of the benefits. And I think that's one of the reasons that I think that's an aspect of programming that people lose sight of when they try to move away, because they're coming from a space expecting programming rather than thinking about how the human interaction works and human-to-human communication. We are. So, yeah.